So this one, we're gonna pick up where we left off last time with accumulation. You're just applying it to an actual scenario. Do you remember the M&Ms? Started with 250 and then we ate some. The party people are arriving and people are leaving. This one is about a gopher and a monkey, all right? So gopher is 10 feet below the surface of the ground. Do you remember what we call that, where they start, what the vocabulary word was? Initial condition. His initial condition is that he is 10 feet below the ground. Do you understand how that's -10? Do you know what a gopher is? Like one of those little burrowing creatures that makes holes in your yard? Okay. So he's below the ground, right below a tree at time 0. So our accumulation does start at 0 for this one. A lot of times when it's a story problem, it starts at 0 because time. All right. Then there's a monkey in the tree. Where's he? +10. He's 10 feet above the ground in the tree at time 0. They start moving towards each other for 5 seconds. That's going to come up later, so just hold on to that. Okay. The speed at which they're moving is given by, all right, G of t is the gopher one. So this is for your gopher. And M of t is the monkey. It says that those are their speeds, which means they are what? Rates, which means they are derivatives. Perfect. We're all on board. And they are in feet per second. So that's sort of analyzing the question. Find the positions of the two animals at time 3. That's where they're at. So we're going to do gopher and monkey. So let's do the gopher first. Where's the gopher starting out? All right, -10 plus, and then we want to do his accumulation. What will be the boundaries on that? 0 to 3. And then the gopher equation is what goes in there. Now hold on, don't reach for your calculator yet. Let's do the other one. How will the setup look for the monkey? What will it be for him? +10. Oh, but he's moving down. They're moving towards each other. So the gopher is like burrowing up out of the ground. The monkey is coming down out of the trees. Good. Do you remember the M&Ms and we subtracted how many got eaten? But that's going to be the same thing, right? 0 to 3 except M of t dt. So we're going to divide and conquer. This half of the room, you're going to do the gopher one. You guys are going to do the monkey one. And you're going to put in that exactly like it looks. And what do you type to do an integral? Math 9. Beautiful. Just make it happen. Go ahead and tap that into the calculator. Radians. Now that only affects you if you're doing trig though. Neither of these have like sine, cosine, tangent in them. So it actually won't matter for this. But yes, you guys want to be in radian mode. All right, gopher groups. What did you get? Good. So let's talk about what that means real quick. Where did the gopher start? -10. So in 3 seconds, he burrowed up pretty far. Gopher. All right, monkey. What did you guys get? All right, 6.7 feet. Think about what that means. Where did the monkey start? 10 feet, but he came down a little bit. Not as fast. Okay. Letter B is a when question, so your answer is going to be a time. When are the two animals traveling at the same rate for the first time? That means they're going to travel at the same rate more than once, but this says the first time. And then how fast are they going? We're not going to do any work for this. That's going to happen completely within the calculator. So here's what you're going to do. Go to y equals and clear it all out. You want to put the gopher equation into y1 and the monkey equation into y2 and just use x instead of t. Okay, so everybody put gopher into one of them and monkey into one of them. It actually doesn't matter which one's which. Alpha y equals will give you that fancy fraction bar, which I suggest using because otherwise you have to fiddle with the parentheses. And personally, I find that more annoying. Now, don't hit go yet. We're going to talk about a window here. If you're not given a window, do you remember what I said to do? If you aren't given one, Zoom 6 will make it standard. Did you guys all hear that there? Zoom 6, it'll put it -10 to 10. We actually were given one though. It says they move towards each other for 5 seconds. So yes, good. You're ahead of everybody else. I'm trying to get everyone together here. All right, so hit window and you want to change your X's 0 to 5. Now, I'm not actually sure what I need the y's to be, so I'm gonna leave them -10 to 10. If I'm remembering this correctly from years past, I think we might need to shrink that down a little bit, but let's just see what we got. Go ahead and hit graph. That's the e to the whatever thing, the curvy kind of thing. Yeah, we're gonna need to bring that in a good bit. Do you see how there's all this extra space up there? So go back to window. Instead of -10 to 10, we need to bring that in a lot. What do you want to try and make it? Yeah, I would even go -1 to 3 because none of the graphs went below the x-axis because they're speeds, they can't be negative. -3 to 3 was a good, I like that you said that. I'm gonna make it -1 to 3 just because I don't have anything negative, so I don't need to see that part of the grid. Yeah, you're good. All right, so do you see how there are two intersections? One's there, it's really tiny, and then this one? You see that? Okay, which one do we want? First one. Do you remember how to make your calculator calculate? It's second trace. Oh, and somebody already said intersect, so do second trace intersect. Now it's going to ask you first curve, second curve, guess. For first curve and second curve, just hit enter. There's only two graphs on there, so you can't be wrong. First curve, second curve. Now for guess, the cursor needs to be closest to the one you want. So for example, if I left it here, it would give me that one. I don't want that. I'm going to keep on going, move it over here, and then hit enter. It just needs to be closer to the one that you want. And then it will literally spit the answer out at you. So let's just make sure everybody can get that. Did you get 0.075? Okay, that's the answer. Time 0.075 seconds. And I have even better news for you. Because what's the second part of that question? How fast were they going? Well, these are the rates. So at that time, how fast were they going? 0.815 feet per second. Good. Beautiful. So not very fast. Although that's almost a foot a second. So I don't know. Letter C says, and this is kind of a trick question. When, so again, it's a time, are the animals closest to each other? It says they move towards each other for, so when are they closest? 5 seconds. At time, 5 seconds. And then it says, how close are they? Here's what I want to have happen. Go ahead and label gopher and monkey. What I want the gopher groups to do, in your calculator, hit the up button until you get this back. Bring it back and just change the 3 to a 5. Monkey groups, same thing. Hit the up button until you bring this back and just change the 3 to a 5. That way you don't have to type the whole thing over again. I'm trying to save you some work. Just change the 3 to a 5 is all we really want to do there. And then you can tell me what you got. We're finding where they are. So unless they were on top of each other, it can't be, that's a good question, but unless they were on top of each other, it can't be the same position. Yeah, they were moving at different rates. So I get what you're saying. That's actually a really good point. Did you hear what he brought up? Won't they be at the same place? If they were moving at the same rate, do you get that they would have landed at the same spot? But they're not because they were moving at different rates. Oh, that's cool. I've actually never had anyone bring that up. All right, gopher people, what did you get? Okay, so here, let's talk about what that means. Where's the gopher? Not only did he burrow out of the ground, he also started to like climb up the tree. All right, monkey groups, what did you get? Right, 3.5 feet. No, that's what we were just talking about over here. They are going at different rates. So no.
Yeah, I feel like they'd be closest to each other. Oh.
No, I'm sorry, they just aren't. I don't know how else to put that. I'm really sorry.
5.5.
Yeah, this says, yeah, like we're not talking about anything that's happening beyond 5 seconds. Our window is 0 to 5 seconds, and we're not talking about anything beyond 5 seconds. So what goes on after 5 seconds is not our problem. Do you get what I'm saying? Like that's, don't try to analyze anything beyond what you get asked. I am kind of telling you to be lazy. Do you understand what I'm saying? Like, don't use brain power to go beyond what they ask you for. Okay. Now it does say how close are they though? So what do you want to do with those two numbers? Yeah, you want to subtract them. So how close are these creatures here? I got 0.751. Okay, feet apart. So they got pretty close. Who do you think's gonna win in the fight? Monkey? I don't know. That's one heck of a gopher that climbed out of the, burrowed out of the ground and climbed up the tree. Okay. Yeah. Okay. I left a little space over here for us to write a few vocabulary words. Do you see how I started over with one? This was on what we did last time. It's kind of like the M&Ms and the party problem. It was just about a gopher and a monkey. We're going to apply this now to particle motion. Here's the pep talk. We're going to use words like velocity and acceleration, but the actual math that you're doing is not any different than this. Do you understand? Just vocabulary that's different. All right. So off to the side here, first vocabulary word we're going to do is displacement. Displacement is where you ended up versus where you started. For example, if I got up out of this chair and ran down the hallway and come back and sat back in this chair, what's my displacement? 0. Okay. Your displacement is integral from A to B of velocity. And I ran out of space there, but it's V of t dt. Integral from where you started to where you ended of your rate. It's always the rate that goes inside the integral. Like we did with the monkey and the gopher. Those were their rates that went inside of the integrals. That's your displacement. Then we've got total distance. Now, if I got out of my chair and ran down the hallway and came back and sat in my chair again, my displacement is nothing, but my total distance is quite a bit of accumulation. Do you see what I'm saying there? What you need to do is treat it all as positive. What happens with the displacement is when I go down there, that's positive, and when I come back, it's negative, and then they cancel out, ends up being nothing. How do you turn it all positive? Oh my gosh, I love you guys. All right, absolute value. So if you slam an absolute value around it, that will become the total distance. You guys all seem to really jump onto that. Have most of you taken physics? Okay, no, just understand it. All right, and then lastly is position, which we literally just did with the monkey and the gopher. It's where you started, which, what do we call that? Well, where we start? Initial condition plus displacement. So it's where you started plus your displacement. Initial condition plus displacement. That will give you where you ended up. So like with the monkey and the gopher, we took where they started and then we added on the integral of how much they had accumulated. Or for the monkey, we subtracted it because he was going downwards. Right? So I'm hoping we can get through number 1 and number 3. I'm going to leave number 2 as a jumping off point, like warm up for next time. Okay, but they have parts to them. So now it's like only 2 questions, but they do have some parts to them. We'll see how this goes. I got like 15 minutes. All right, the graph to the right shows what? That's good. You want to be given velocity. Velocity is your source that gives you all your information, right? Particle is moving from time 0 to 11. There aren't any units here. Consists of a semicircle and blah, blah, blah. Let's go find all our areas. How would you get the area for this part? All right, 1/2 pi r squared. What is that? 2 pi? 2 squared is 4. Half of 4 is 2. 2 pi. All right, then you have this huge triangle. 1/2 base times height. The base is, let me count them. 1, 2, 3, 4, 5, 6. And then the height is also 6. 18, but it will actually, good, it'll be negative 18 because below sea level. And then this last little triangle here, 1/2 base times height, that would be 1/2 times 1 times 3, which is 1.5 or 3/2, whatever suits you. I went with the decimal on this one. So letter A says, find the total distance traveled from time 0 to 11. Do not jump right in and say the answer. Set it up. It'll be 0 to 11 of what? Good. Absolute value, V of t dt. Oftentimes on the AP exam, writing that is worth a point. And then the answer is worth a point. And you don't want to lose a point because you didn't write that. Okay, so what we're gonna do is add together all these areas, but treat them all like they're positive. So it'll be 2 pi plus what? 19.5. You treat them all like they're positive. Or is that what you said?
Yes.
Oh, okay, I just couldn't hear you. All right, B says find the value of that and explain what it means. Okay, so now you're gonna add them all up, but don't treat them all like they're positive. Just what they are is what they are. So that would be 2 pi minus 16.5. And then we have to write a sentence. So that is, and what vocabulary word did I use up there for what? Perfect. Displacement. And I'm going to show you how you'll write it when there are units. This one just didn't have any. You would say displacement in time units. So you would say displacement in, oh, no, I'm sorry. Distance units, I'm sorry. It would be like displacement in feet or something. So you'd say displacement in feet from when to when? Yep, from 0 to 11, and then you would put like time units. So your sentence would be something like, this is displacement in feet from 0 to 11 seconds, or this is displacement in miles from 0 to 11 hours is how that sentence goes, okay? If the initial position is 2 at time 0, but it's not always 0, all right? So just be careful if there's a different number there. Then find the position. So it will be 2 plus, I'm gonna set it up exactly like the gopher and the monkey. In my opinion, the problems are easier when there's a story. I don't like when there's not a story because it's like, what on earth is going on? All right, it would be 2 plus integral 0 to 11 v of t dt. So that would be 2 plus, hey, we already found that in part B, 2 pi minus 16.5. Just for the sake of being thorough, that would be 2 pi minus 14.5. And then again, it would be like yards, meters, feet, miles, whatever have you for that. I'm going to leave number 2 as a warm up for next time. I think it's the hot air balloon problem, correct? We actually did this exact problem way back when, before you had learned what an integral was. We're revisiting it with the integrals in there. See how much you remember of that. But I'm going to use that as a warm up for next time, because I think we could finish this whole one.
Yeah,
All right.
come out in class, I remember being in it.
Oh, I'm sorry. Don't be anxious about it.
Well, that was.
Okay. The table below gives values for what? All right, velocity and acceleration for a particle moving in nanometers. I made this up just to be silly. And to keep you on your toes, because we usually use feet and seconds. So I made it nanometers and decades, all right? Both velocity and acceleration are differentiable functions of time. Velocity is decreasing for all values. That's going to come up, all right? They don't tell you that for no reason. Decreasing from 0 to 10, use the data to answer the question. Anytime you get given a table, you want to be like, yes, because you don't have to do anything with a function. There's no button pushing with a function. Like all the numbers you need are right there. Isn't that great? In fact, a lot of those numbers are probably numbers we don't even need. You know how they give you extra stuff? All right, your world is very small. Use a left Riemann sum to approximate this. All right, how many sub-intervals do we have? 3. Good. Are they all uniform? Bummer. All right. What's the length of the first one? Right, 2. And then you want the number on the left for velocity. See how it's velocity in there? So 5. Plus, all right, what's the next one? 4 times 3. Perfect. And then the last one, 4 times -1. Perfect. Show the computations you used to arrive at your answer. We just did. Explain what it means. There's not an absolute value. So this is what? Good. Is displacement in nanometers from 0 to 10 decades. I did it to be silly because we remember stuff that's funny and we forget stuff that's boring. It's moving in nanometers per decade. It's funny. Get on board, all right? Is that approximation greater than or less than? So is it an over or underestimate of the actual value? Now we said velocity is what? Just watch. Decreasing would look like this, right? Did we do a left or a right sum? Left. Do you see how the left side is higher up? So we're going to say overestimate because, and then basically just paraphrase what I just said. Because what? Well, we're going to say left sum, but and if you say it, they won't give it to you. Velocity, good. And you can write V of t is decreasing, and this is a left sum. You were kind of going above and beyond there. The left side is higher up than the right, so you don't need to say all that. And you want to be as succinct as possible because the exam's time. Overestimate because velocity is decreasing, and this is a left sum. All right, what does this mean? Not displacement, but the other one. I like that. Total distance. Here's the thing. You have to treat all the numbers like they're positive. If you forget and you write them as negative, you're not going to get the points. All right. Also, what type of sum did they say to do? So, okay, here we go. 1/2. What's the length of the first one? 2. And then you have to add these together. So 5 plus 3, and don't write 8, write 5 plus 3, because that's the show your computations that lead to your answer. They want to see the whole thing, all right? Plus 1/2 times, what's the next one? 4, and then be careful. It's 3 plus 1. You have to treat them like they're positive. Absolutely, I know. All right, and then the last one, 1/2 times 4, and then 1 plus 8. Good, but you don't have to do anything with that. But it does explain what it means. It's the exact same sentence we wrote in part A, except instead of displacement, you're going to write total distance. Blah, 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 blah is the total distance in nanometers from 0 to 10 decades. The exact same sentence, just recopy it, but instead of displacement, put total distance. I like that. What is this one? Not displacement. The other thing. Cool. I have enough time to finish part D. This is exactly what I wanted. All right. Determine the value of that thing. I know it seems like you might be reaching for those A of t values in the table, but you're not. Do you see how this one says approximate? And then this one says approximate. And this one says approximate. The reason we're approximating is because we don't have an actual function. All we have are those values in the table. This one says determine the value. It's not going to be an approximation. If you do an integral, an antiderivative of acceleration, that takes you back to velocity. Let me piggyback off of that. If you do an antiderivative of velocity, that takes you back to position. Good. Okay, so it's velocity such that, fundamental theorem of calculus, 0 to 10. Beautiful. Upper boundary minus lower boundary. So it's v of 10 minus v of 0. We never used any of those acceleration values in the table. Those are all there simply to throw you off and confuse you. Tables are great, but that's the one thing they do a lot with them is put extra stuff in it that you don't need. All right, what was v of 10? Just go grab that from the table. -8 minus v of 0 is 5. So what is that? -13. Now it says to explain it. That's negative. So that means velocity is what? Velocity decreases 13 nanometers per decade. And then you have to say one more thing. It's not at, in this case, it's from. I know what you mean, because usually it's like at time, whatever, but an integral is over a period of time. So if you were thinking at a time, you're thinking the right thing. All right, from, I think I made that one 0 to 10. I think I made them all 0 to 10. So not only is this thing moving at a glacial pace, it's also, yeah, like moving less